Hi, my name is Pedro Paredes from Carnegie Mellon University, and in this talk, I'm going to tell you about spectrum-preserving short-cycle removal on regular graphs. Let's jump right in. The objective of this work is to show how to modify a regular graph to obtain a desired property, namely a certain girth, while preserving both the regularity of the graph as well as its spectral properties. We'll do so by doing some surgery, meaning we'll remove some edges and add some extra vertices and edges. But first, let's quickly introduce some notation we'll need throughout the talk. Let G be a graph with n vertices, with vertex set V and edge set E. We will concern ourselves with irregular graphs, that is, graphs where every vertex has the same degree d. Our focus is on spectral properties of graphs, so we need to consider adjacency matrices of graphs, matrices where rows and columns are indexed by vertices, and an entry of the matrix is either 1 if to the two corresponding vertices are adjacent, or 0 otherwise. We'll denote this matrix by A. We'll also denote the eigenvalues of A by lambda. Anytime we mention eigenvalues in this talk, we'll be referring to the eigenvalues of the adjacency matrix of some graph. Finally, it's important to mention that all graphs we'll use are undirected and unweighted, which means their adjacency matrices are 0, 1, and symmetric. Okay, now let's review some well-known facts about eigenvalues of the irregular graphs. Since A is symmetric, it has n real eigenvalues that we can order as such from 1 through n. The largest eigenvalue, lambda 1, is always d, the degree of each vertex. The graph is connected if and only if lambda 1 is strictly greater than lambda 2. And finally, lambda n, the smallest eigenvalue, is minus d if and only if the graph is bipartite. So the first object we're going to need to describe are expander graphs. These are graphs where every small set of vertices have many edges on its boundary. More formally, the edge expansion of a graph is governed by this expression over here. This ratio compares the number of edges leaving a certain set of vertices, or equivalently, the cut they induce, and the number of vertices in the set itself, like it's depicted in the picture on the left. If the edge expansion is large, that means that every set of vertices has a lot of edges that leave that set, like we can see here on the picture on the right. Sparse graphs that have high edge expansion are called expander graphs and have many applications in math and computer science. I'm going to let you stare at this slide for 1 second before I move on. Okay. The spectral expansion of a graph is given by this quantity lambda over here, which is the maximum between the second largest and the smallest eigenvalue in magnitude. This quantity is closely related to the edge expansion we just saw. One way to see that is through Cheeger's inequality. In a nutshell, it implies that whenever the spectral expansion is small, the edge expansion has to be big, and vice versa. The expression itself is not super important for us. We just care about this correlation between the both expansions. Finally, we can define a family of expander graphs as an infinite sequence of graphs with increasing sizes, where the spectral expansion of each one is bounded away from d, its maximum possible value. But now we can ask, how small can lambda be? A result known as the Elan-Bopana bound says that it can be arbitrarily small. It has to be at least 2 square root t minus 1 minus a small quantity. This value of 2 square root t minus 1 seems quite magical, but it actually has a very interesting reason to be so, which I encourage you to look up, but unfortunately we won't have time to look over in this talk. Given this result, we define Ramanujan graphs as optimal spectral expanders, meaning graphs where the spectral expansion is at most 2 square root t minus 1. And now we can ask a second question. Do Ramanujan graphs exist? And if so, can we construct them? In the 80s and 90s, Lobotsky, Phillips, and Sarnak, and Morgenstern show that the answer is yes, if the degree d is 1 unit more than a prime power. More recently, Marcus, Spielman, and Srivastava and Cohen show that if we only care about lambda 2, the second smallest eigenvalue, we can construct bipartite one-sided Ramanujan graphs, meaning they only bound lambda 2. Even more recently, Mohanty, O'Donnell, and myself, and also Alon, show that if we only settle for new Ramanujan graphs, meaning graphs where lambda is a small epsilon away from being optimal, then we can explicitly construct such graphs for all degrees. And again, I'll let you stare at this for 1 second before we move on. Okay, so let's now turn our attention to the main topic of this talk. Let's suppose that we're given an n-vertex irregular graph G with spectral expansion capital lambda. And from this, we want to construct a new graph G prime, whose spectral expansion is almost the same, but it has some additional property, which is that we removed all small cycles, or rather, that it has large girth for some definition of large that we will see in a moment. The key idea for this construction is that good spectral expansion is loosely connected to the scarcity of small cycles. This will make more sense in a bit. But before we make this more formal, let's define bicycle freeness. A graph is bicycle free at radius r if for all vertices v, there's at most one cycle per ball of radius r. You can look at this picture over here to have an intuition of what that means. Okay, so now our revised goal is the following. We're given the same n-vertex irregular graph G with spectral expansion capital lambda, but we assume that is also bicycle free at radius r. And for simplicity, let's just assume that r is around log d minus 1 n. And now we want to construct a graph G prime, whose spectral expansion is almost the same, but the girth is at least r. As a bonus, we want to do it explicitly, meaning we want to find G prime in polynomial time. We won't address this last question here, but the construction we'll see also has this property. This is the main contribution of this work. We'll see how we can apply it to some problems very soon. But first, why should we care about bicycle freeness? Why is this an interesting initial condition? It turns out that it's a common property of deregular graphs. We know that a uniformly random deregular graph is near Ramanujan with high probability, but it is also bicycle free at a large radius with high probability. It's also no surprise then that this was used in the previous work that we mentioned that constructs explicit near Ramanujan graphs. And this construction also gives that the resulting graphs are bicycle free at a radius not as high as the uniformly random result, but actually just square root of log n. And so we conclude that this bicycle freeness property is actually a prevalent property in deregular graphs. Additionally, it is easy to show that if a graph is bicycle free at a certain radius r, then it cannot contain too many cycles of length up to r. And the proof of this fact is actually just a simple ball growing argument that we won't see here, but you can think about it. Now let's look at what we can use this main theorem for. So recall that a uniformly random deregular graph is near Ramanujan and also bicycle free at a large radius with high probability. If we apply our cycle removal theorem, then we get an explicit distribution of near Ramanujan graphs with high girth. Again, I'll let you stare at this for 1 second before we move on. And we can do the same thing to the explicit version of this result. We can get an explicit construction of near Ramanujan graphs with girth of square root log n by doing the exact same thing. And again, I'll let you stare at this for 1 second before we move on. Okay, let's briefly outline the proof of the main theorem. Recall that we're given the same n-vertex deregular graph G with a spectral expansion of capital lambda, and we assume that it's bicycle free at radius r. And now we want to construct a new graph G prime whose spectral expansion is almost the same, but the girth is at least r. Okay, and here's our construction. First of all, we'll break up all small cycles by listing them and then selecting one edge per cycle. Let's call E sub c to this list of edges. And we further partition the endpoints of these edges into two sets v1 E sub c and v2 E sub c. So again, we'll select one edge per cycle, and we call E sub c to this list of edges, and we partition the endpoints into two sets, v1 E sub c and v2 E sub c. Now, we need to pick a lot of extra edges that are far apart. Namely, we need to pick edges that are distance r from each other, and from each of the edges in the previous set E sub c. And we place them in a new set E sub t. So we're picking new edges and putting them in the set E sub t, such that each edge is far away from each other edge that we picked, but also from the edges that we picked previously, the edges in E sub c. Okay, now the third step is we're going to remove all of these edges in E sub t and E sub c from our graph. And since we break up every small cycle, the resulting graph is girth at least r, like we wanted. However, we might have some vertices that have off degrees, because we removed some edges. So all the vertices that were adjacent to some of the removed edges have off degrees. So we need to fix this by adding new edges strategically. And this is our final step. We're going to do that by adding two deregular trees with height around r, and we're going to merge the leaves of the off-degree vertices in blocks. Or we're going to merge the leaves of these trees with off-degree vertices in blocks. So note that each two of these trees that we add adds fresh vertices to the graph, with the exception of the merged leaves. And now each block that we're merging will contain one vertex from V1 E sub c, meaning an endpoint of an edge we removed to break up a cycle, and lots, namely d minus 1 to the power of r over 2 vertices from V1 E sub t. These blocks are constructed in this way because we want to ensure that we don't create short cycles that route through these two trees. And so again, we're merging the leaves of two trees that we added with the endpoints of the edges we removed. The tree on the left, T1, the leaves of the tree on the left is merged with the endpoints in V1, EC, and E sub t, and we mirror this with T2. We merge the same vertices and the same leaves with the vertices in V2, or the other endpoint of EC and ET. Okay, and we do this in blocks. Each block has one edge from, or one endpoint from E sub c, which means one endpoint from an edge we removed to break up a cycle, and a lot of vertices from V1 E sub t, meaning an endpoint of the remaining edges we removed. And we repeat this block structure until we merge every single tree with every single vertex of off degree with the leaf from this tree. And obviously we have to be careful with the amount of vertices and edges removed so that this all matches up. We won't look at that, but it's possible to remove the perfect amount of edges such that we can match every single edge, every single vertex with a leaf from one of these two trees. Okay. Now, it's easy to see that this construction ensures that the resulting graph is irregular. It has O of n vertices, and it's actually explicit. Now, we need to prove two claims. First one is that the resulting girth is large enough, and the second one is that the resulting spectral expansion is good enough. We won't have time to look at the second claim. You can check our paper to learn the details. But we're going to briefly sketch the proof of the first claim. The main idea is that there are only two types of cycles that we can create by adding these two trees. Recall that the vertices from G, so from the original graph, have no small cycles because we destroyed every single small cycle by removing those edges. But the trees might add some new cycles that could be small, so we have to show that that doesn't happen. But there's actually only two types of cycles that we can add. The first type routes through leaves merged with vertices in V1 E sub c, so endpoints of edges that were removed from cycles. Because of the way we built our blocks, such a cycle needs to go deep into the tree, and so needs to be of length larger than r. This picture sort of represents that. Because of the way we merge the vertices with the leaves, we might have a short connection between a leaf from T1 and T2 by using the remaining of the cycle that we broke apart, but in order to complete the cycle, you have to go deep into T1 and T2 in order to leave through another vertex in V1 E sub c, and because we made these blocks very large, we have to go very deep into both of the trees, and so the resulting cycle is actually of length at least r. The second type of cycle that we can create is a cycle that routes through a leaf merged with a vertex in V1 E sub t, so the remaining edges the remaining endpoints of edges we removed. But because we chose these edges to be far apart from every other edge, In order to close a cycle like this, we need to walk through at least r steps. We need to walk at least r steps in G. So the cycle will be of length greater than r. This was just a sketch of the proof. For more information on how this proof actually works, you should check our paper. And that's it. The key things you should take from this talk are that first, good expansion and scarcity of cycles are loosely connected. Second, we can modify regular graphs by preserving the spectrum if we only alter blocks of the graph that are cycle-free or that have very small number of cycles as long as we destroy them. And finally, we can use this to construct new Ramanujan graphs with high girth. And that's it. Thanks for watching.